Hello, thank you for joining our webinar, Open M-SDL for Scenario-Based Verification of ADAS and Autonomous Vehicles, Introduction, Developments, and Applications. I'm Karen Rogachevsky, Director of Marketing at Fortelix, your moderator for this 90-minute program. M-SDL, Measurable Scenario Description Language, is the first automotive-specific verification language designed to define specifications, coverage goals, and scenarios in a human-readable, measurable, and reusable way. The language was initially released last September, and since then, over 500 engineers from 250 different entities have already downloaded its specification, and it has been adopted with various applications. We are happy to host you on this webinar, where we will share with you both the basics of the language as well as new and advanced functionality. Our agenda for today includes an introduction to M-SDL, followed by a demo of the usage and application of the language. We will then move on to cover M-SDL recent developments and talk about ASAM standardization efforts and the connection to M-SDL. We will end our program with an audience live Q&A, so please send questions at any time through the Q&A box. I would like to introduce our speakers for today. Yoav Hollander is the founder and CTO of Fortelix. He also writes a blog about various verification topics. Yoav is a world expert and leader in verification. He invented the e-verification language, IEEE 1647, and related methodologies. In the last few years, Yoav has been researching the verification of autonomous systems. He also represents Fortelix in the ASAM standardization body in the OpenSCENARIO 2.0 project. Sharon Rosenberg is a methodology fellow at Fortelix. Sharon is an expert in complex verification methodologies with 23 years of experience. Working for Cadence in the past, Sharon was a lead architect of several standard languages and verification libraries, such as the IEEE UVM standard and the Accelera PSS standard that are the mainstream practices in the chip design industry. Sharon authored the book, A Practical Guide to Adopting the Universal Verification Methodology. And now, please join me in welcoming our first speaker, Sharon Rosenberg.
Thank you, Karen, and thank you everybody for joining. So it's hard to talk about ADAS and AV verification without mentioning street driving. Let's see. I don't get, here we go. I have control back. So the AV industry initially put a lot of focus on physical driving with test fleets, and there's good reasons for that. I mean, this kind of testing is accurate. This is real world tests that we're trying. It's also verified the entire car itself, whether it's the engine, the brake system, the radars, the sensors, everything is under test. Things are also well prioritized. So things that happen typically or more often will be verified first. So with all the advantages, there are some also drawbacks. And for example, this is not always effective testing. So yeah, you're going to get the typical behavior more and more, but you'll get a lot of it. And this might not be as productive for your verification efforts. Lack of measurement is something that the industry discussed for a long time. 1,000 mileage in Nevada is not the same as 1,000 miles in downtown San Francisco. And talking to existing customers that have done it before, they're saying that sometimes they do a lot of mileages. They don't know if they're just starting to scratch the surface or maybe they even done. So there is lack of confidence in mileage. And street driving can also be dangerous for property and for lives, obviously the driver, but also pedestrian and surrounding environment. Once you realize some condition or concern was not exercised, it's really hard to target and get to exercise it in a synthetic way. One of the biggest drawbacks of street driving, it's not effective for rare and unknown conditions. So some things that we may experience once in a lifetime, given enough cars, could happen every 5 or 10 seconds, minutes. And That is a hard thing. I mean, this could be dangerous and risky conditions. Street driving also very high cost. It's very expensive, those cars, and you may need to ship them to various ODDs and locations. So in summary, street driving, that's important, that's mandatory, but it's not enough. And we do see trends of company move the focus and find the right balance of street driving and synthetic tests. So how is synthetic tests achieved today? There's no single answer. The answer vary across teams and tools. So typically a system architect will create the test intent in English, and then test writers will create the test themselves. They might program it using a program, but then we'll have to spend a lot of manual effort of creating concrete scenario, carefully selecting the values to make them legal and consistent. You can also use GUI tools, and basically you select a location on a map and draw the scenario. The drawback here is, things like loops or conditional control flow. Or if the ego did that, I want to react like this. This is hard to specify with a GUI. There's another starting point of starting from recording data and take it from there. Now, some solution provides variations. These are systematic walk over a given range of values for one or more parameter. Let's analyze that with this example. I'm going to use that cutting and slow example throughout the presentation. It works like that. The first thing in our AV is in red. The first thing is the ADAS car. The NPC is going to get ahead of the AV. Then it's going to cut in front of it, and finally it's going to slow. Now I may want to specify variation to that abstract scenario. So I may change the distance, maybe the lateral distance from which the cut-in is going to start. The deceleration, I can decelerate fast or slow. And the speed, it could be the relative speed, and it could be also the absolute speed of the ego, the NPC car, etc., the other car. Now, major issues, and we hear that a lot from our customers, that once you generate the variations, there's a lot of work after the fact to actually filter what is legal and what is interesting. So it's not that the entire space is legal or interesting. And there's teams of people working on filtering and qualifying each and every concrete scenario that was randomized. There's also manual effort required to measure if the actual intent was met. Obviously, the AV might change its behavior, and then the distance that we thought we're going to get was not the right distance that we actually got. So that there's a lot of work to qualify those scenarios and see if the coverage metrics were met. One big concern for the entire industry, and it's specified in SOTIF and explicitly said by users themselves, there's no way to address the unknowns and the unexpected. The systematic walk, just go over things I asked for. What about the things I didn't think of? Can we address that somehow? Here's the high-level description of the solution. So in a funny way, we're not going to create the scenarios. We're not going to write them. Technology is going to do that. We're just going to capture high-level scenario, very, very abstract, and rules for correctness and rules of what is interesting and what are my goals. Then technology is going to read that, process that, and create tons of variations, massive amount of tests, which complete and take these rules into account. So you get multiple location generated circumstances and distances, etc. That is going to be generated as much as you want them. You can generate more and more given that technology exists. The last step, you're going to look at the coverage and see what kind of, the kind of things you tried are in green. That's, I've tried that. In yellow, you see things that maybe were partially covered, and in red, things that were not covered. So I actually get to see, given the unpredictable reaction of the ego, what really happened. And if I need to close some gap, like it was partially covered or not covered at all, I'm just adding another rule. Hey, go to this area and give me more tests like that. And this could run on top of multiple execution platforms, simulation, hardware-in-the-loop, test track, and test driving. Let's kind of look at the flow. This is the metric-driven verification flow. So the first step is creating a plan. And I'm sure all of you create a plan. And if you seriously create a plan, you probably realize that the best way to create it is in hierarchy, right? We create some high-level concern, and then we break the high-level concern into sub-concerns, and et cetera, et cetera. What's going to be unique in this flow is that the plan is going to be machine readable. I'm actually going to read the plan in the last, in the last step in here and see what was achieved and what is not achieved given my simulation. The other thing is that you can be more ambitious. If you create concrete scenarios manually, you can ask for 1, 2, 5 scenarios. But now since automation is in place, be more brave. I mean, ask for 100 or 1,000 for each concern that you have, and the technology is going to do that. Like we said before, you're not really writing the scenarios. We're going to create some kind of abstract partial description scenario, and the technology is going to complete that in multiple ways. The main engines of the M-SDL tool is a constraint random generation engine. This is a constraint solver, which is going to create many multiple concrete scenarios. And then you're going to run them on the third step with a simulator. Another engine is a self-checking, which is just going to indicate if the ego react as expected. And the last one, we're going to get a report, a customized report of what was covered and what was not covered. So in the fourth step, you're just going to look at the report like we've seen on the previous slide. And basically, you have these options, either that you're done or you're not. So you may want to put more rules to steer the randomization to areas you haven't tried. And another one is, since this is random generation, the tool may come up with scenario you didn't think of, and maybe there is a category of scenarios that is hiding there. So you may want to refine the plan and create a new category and basically create a new family of scenarios going to that randomized achieved direction. So that is the entire flow, and you will do that in iteration till we're done. Let's say a few words about OpenSCENARIO 2.0 and M-SDL. So ASAM, for those who don't know, this is Association for Standardization of Automation and Measuring System. It's a non-profit organization, and it's very talented, ambitious engineers there that basically contribute to the benefit of all of us. So they do a lot of good standardization, and OpenSCENARIO 2.0 is one of them. OpenSCENARIO 2.0 allow to describe the abstract scenario with all these rules that we just mentioned. Many of the concepts of OpenSCENARIO 2.0 comes from M-SDL, but there's also influence back. So actually OpenSCENARIO 2.0 influenced M-SDL, and Yoav is going to talk about that as well. This is quite big. Standardization body. There's more than 290 members in there, and we highly recommend joining, learning, and contributing to that important work. This is just a quick glimpse on the timeline of OpenSCENARIO 2.0. We're done with the concept project, so there's a formal official paper of what the concept of the standard is going to be. That's happened on March, and mid-2021, this is where we predict we're going to come up with the standard release itself. Note that like the ASAM proposal workshop, since OpenSCENARIO 2.0 does not exist yet, they use the M-SDL for demonstration, and this is what we're going to do today as well. So we highly recommend joining. Like I said before, just go to asam.net. Let's talk about the language itself. So this is an open, non-proprietary language. You can take it right now and create tools and technology on top of it, and it's geared to capture scenarios. It's a good combination of power readability and composability. So you can actually look at the code, even if you don't know any programming language, pretty much can understand what's going on. It's declarative and extendable, and I'll talk about that. Allows expressing rules in a declarative statement way, and basically translation the plan specification into a machine readable code. The scenarios have dual interpretation, could be both active and passive. So I can actually ask for something to take place, but I can passively monitor maybe a chaotic scenario and tell you if this ever took place, that this scenario ever took place. The scenarios themselves are portable across testing platform, like I mentioned before. Level of abstractions, I can be very concrete, very, very abstract, or anywhere in the middle. I can layer ODD restrictions very easily on top of this scenario. It's one line of code to change maps. And it's also portable across teams and use model, which make them excellent bridging technology because all these teams are able to read that intuitive description. So if you haven't seen M-SDL before, this is how the language look like. Here we're using Python syntax and lexical conventions, so indentation does matter. And you can define in actors, which are elements of the world, and their behaviors with actions. And let's look at this example. We have a vehicle in here, and it has a category, which could be a sedan, truck, or a bus, and it has a length, which is a distance of type distance. And here is an action, which is just drive, and drive may have attributes as well, which is speed of type velocity. All the attributes by default are randomized unless you limited that. And what we're trying to achieve is basically explore the unexpected. You'll see that once you randomize some activity, you get some unexpected combinations here. Now, like we mentioned, not all the variations are legal. So how can I put a limit on the vehicle side? And here's a constraint, our first constraint. We're just saying keep the length is smaller than 10. Here's another one. If the category is a truck, this implies that the speed is smaller than 80 kilometers per hour. Now, if I randomize many, many drives of many, many vehicles, I'm going to get legal and consistent solution. The speed is always, in case of a truck, will be smaller than 80 kilometers per hour. Let's look at the first verification plan item here. I want to drive at speed 20 to 100 and later drive at speed faster than 90 kilometers per hour. So this is what you see here. So serially, that's a behavior of a scenario. Do a drive with speed between 20 and 100 and then do a drive with speed larger than 90 kilometers per hour. Now look at that composition. The tool is actually making a lot of inferences for us, things that we may have to calculate in our heads and code on our own. The tool is going to do that. For example, I can tell you for sure that this drive will never be executed by a truck. Why is that? Because we're asking the second drive to be, the speed to be larger than 90 kilometers per hour. And we know that trucks are limited to 80 kilometers per hour. So the tool will do all that analysis and just provide legal variations and control here. Let's look at a more interesting plan item. This plan item is a head and stop, and what we're going to do is drive the ego to some location. The NPC will arrive to that location 0.5 seconds ahead of the ego, and then it's going to stop. Someone decided that this is a very good exercise for our ego, and that's what we want to execute. Now, if you look at that plan, it just said the things that must happen, inviting the test writer to complete that. And this is what you do without M-SDL, right? You're first going to select a location on the map, and you need to choose the right location that will match what needs to happen here. Then you're going to estimate the ego speed and coordinate the NPC location at the proper speed to get there 0.5 seconds ahead of the ego. Once you do all the calculation in your head, you're probably going to program or draw that using a GUI. And then you're going to visually inspect that you actually get the intent that you wanted in simulation. And if you didn't, you just debug with a source level debugger and fix things to get what you're after. This kind of effort is needed for every concrete scenario you're going to make. You'll have to do it over and over. You might be a little bit smarter on your second concrete scenario, but you'll still have to do it over and over again. And in the future, once you put it in a regression, you wouldn't even be able to tell if this intent is still being preserved. I mean, if you change the software stack and the decision of the ego and the reactions are going to be different, you cannot even tell if this expensive, hard to achieve scenario is still doing what it's supposed to do. So that's a lot of work, and we'll have to do it over and over again. Let's look at the M-SDL solution. So look what we're doing in here. So in parallel, the ego is going to drive, minding its own business, and serially the other car is going to drive, and look at what we're saying here. The time needs to be 0.5 seconds ahead of the ego. and then stop, which is driving at speed of 0. Look at the translation here between what was asked for and the code itself that could be read by a machine. And now the machinery will do most of the heavy loading for us. It's going to select a random location. It might be in the middle of the street, in front of a parking lot, in front of a building, but it can surprise us in multiple ways, and still it's valid for the requested scenario. It's going to calculate all the speed and the starting point of the other car to be at the right time. Now, since the ego is going to change its behavior in runtime, we're actually going to make the other car change its behavior accordingly to try to nail. So the technology is actually working for us in runtime, adjusting the circumstances to nail what you're actually asked for. Eventually, we're going to output a report saying if we got it or didn't get it. If you didn't get it, just do it over again and try to get it. Now, this kind of scenario is adoptable to new software or specification changes. It might do totally different planning. The runtime adjustment might be different, but you will see in the report if you're achieving what you're achieving. And that's an important thing. So again, if you look at that kind of a code, it's simple to achieve, very productive, and you can create millions of scenarios like that. That's going to be, there's a lot of cost saving with using that approach versus manually creating each concrete scenarios at a time. M-SDL is very good with splitting the task between scenario developers and test writers. So scenario developers, this is a smaller team that have more expertise in M-SDL, and they're going to create reusable scenario, maybe leveraging existing scenarios. Test writers, there's going to be much more test writers. They're going to write simple tests, and we'll see an example of that, and then going to observe the coverage and see what was verified and what was not verified. And then they're going to encourage the automation to get more of the non-verified conditions. So they don't need to know a lot of M-SDL. They can achieve tons of scenario, but just asking the technology to generate it. And Yoav is actually going to mention how you can create tests even without knowing any M-SDL. So we're not going to give you a discount today. Let's first look at so-called the hard to achieve scenario. And I hope I can convince you, well, that is pretty simple and not that hard anyway. So here's a cutting and slow that we've described before. So I'm instantiating the actor is the car. And here's a side attribute of this scenario because the cutting could go from left or right. And here's the path. That could be multiple attributes to the path, which are going to be randomized. If we're eventually going to randomize the location. And here's how you say it. So here, the ego is going to drive 30 to 70 kilometers per hour. And then our car, the other car, is going to start 5 to 100 meters behind the DOT. Then it's going to finish 5 to 15 meters ahead of the DOT. Later on, it's going to do the cutting, starting from the side of the DOT and ending at the same lane. And eventually, this is the deceleration. You can see that we're doing a speed change in here of -10 to -15. So that's it. That's the description. There's tons of solving going on and figuring dependencies to create that solution. The tool is going to read the entire scenario and plan legal combination of attributes that will nail that intent of cutting and slow. So first of all, it's going to randomize location, and you'll be surprised what kind of locations you're going to get. And it's going to tailor the scenario according to the location. All these attributes that are marked in red are randomized. Think about how many things and how much unexpected is being created here. This is a goal-based approach. I'm saying, oh, I want you to be at the end or at the beginning of a phase, behind or at the same side, at the same lane as the DOT, etc. And the tool will make it happen. It will fulfill the scenario according to your request. This one is, this scenario is ODD independent, right? I can run it on any ODD. It's also very easy to add ODD restrictions, to layer ODD rules on top of that, and then you'll get just scenarios of cutting and slow that make sense and interesting for that specific ODD you're focused on. Now, if you didn't ask yourself, you should have, how do I get to that specific location, both the ego and the other car. And what the technology does, it's going to insert implicit action to get to that location. This is very important for productivity because now I can get a lot of random ways of getting, and this can surprise us in multiple ways, but also for reuse, because if I want to do cutting and slow and maybe do it at the same time with other scenario, if I went through all the trouble of specifying how do I get to that location, and I went through all the trouble of getting to a different location for the purpose of a different scenario, I cannot put them together. These two preparations will collide. So what the technology does in here is just going to insert implicit action for the composed scenario. So things are more modular and reusable like that. When the tool will just tell us what you want, we're going to insert the implicit actions as needed for the specified scenario. Like we mentioned, there's runtime adjustments going on here, reacting to the AV unpredictable reaction. So just to summarize, this is something that the developers, scenario developers, are going to use. And look, it's pretty short, it's pretty intuitive. I think that all of you can create such scenarios. Now let's look at the world of the test writer. We're just going to select, this is what the developer created. They're just going to select, encourage, and steer the randomization to some areas. So for example, I can just, do a cut-in and slow with a side equal to the right, because most of the cut-ins will happen for the left. Maybe I want to have a rule like that. Or in another abstract scenario, I can say, well, serially do that. Go cut in from the left, then right, and then left, until we'll do what you ask for. Or repeat 5 times of cutting and slow, and the car color different than green. You just do whatever you want, and you can ask for as many variations as you want for that specific scenario. Now, when you typically devise with some procedural language, if you want to prepare a test writer interface, you're going to factor out a few parameters and give that to the test writers to control. But M-SDL is much more flexible than that. I can actually go into internal attributes here and put constraint on them, expecting the technology to adjust the rest of the scenario to my specification, to my will. So here's an example. What I'm asking here is, in change lane, I want the speed to be 7 km/h. And now the tool is going to build the rest of the scenario around that request and create many of these. If it makes sense, it could, by the way, tell me, you cannot do that because there's other constraints and rules from the cut-in and slow or something to do with the car that make your request impossible. But that's everything you'll have to write. Look, the code are very short. You don't need to know a lot of M-SDL to create some scenarios. So this is very easy to create. And again, Yoav is going to show you something, how you can create that kind of scenarios without knowing any M-SDL. So we created those scenarios, and now we can create many of them. And, we can just sit and enjoy the view. You can see that there's multiple cuttings, different view, different locations, and this could be very enjoyable, but just for a limited amount of time. I mean, you're not going to look at million scenarios and see, well, did they actually get what I wanted or not, right? So how do you know if you check enough? And, what if the locations or the ego reaction change? Does it still doing what it's supposed to do? So how do we decide when we're done? So this has to do with the dual interpretation that I mentioned before. Look at the scenario cut-in and slow. You can look at it as a recipe to the test, to the M-SDL tool. Please make that scenario happen. But you can look at it as a passive observer. Tell me if this scenario ever happened. And of course, this will take into account the DUT responses, the unpredictable DUT responses. But I may want to know not just if this happened and how many times. I may want to know, well, did it happen from the right or from the left? And on what path did it happen? And what kind of cars were exercised, etc. I may want to even cross combinations. I want to try all deceleration speed with car categories. So there are many things I want to specify. And how do you do that? Very easily. There's coverage features in M-SDL that allows you to capture and record what you're interested with. So here it is. I'm saying cover the side. You know, I want to get both left and right. The car category, here's where I ask for cross combination. Cover the side cross with the car kind, and I'll get all the combinations. Sometimes I'm not interested in a specific value, but I more care about the ranges of values. I want to make sure that I'm trying between 10 to 20, enough samples. I want to try 20 to 30 and so on. Very easy to specify, and you can go to whatever detail you want, and let's read this together. So the only thing I want to sample is the speed at slow.start phase, and I want to cover all the values between 10 to 130. Every 10 will get its own buckets and its own range. So you can actually express exactly what you want to have as a goal to be reached. And the tool is going to automatically, in a passive way, capture that information for you. So, and of course, this is very useful if you're going to use it passively, and you can do that from all the execution platforms. Read that in, get the result on top of your user-defined goals, the goals that you set up as goals. Before we go into the demo, just want to show you one more very powerful technique to address the unknown. So we kind of touch the unknowns a little bit with the random selection. Everything is random. I'm not biased in any way. Technology is just good. You uniformly select from the entire legal space. So what are the unknowns? That's impossible to fully define, obviously. But when you look at a very surprising, unexpected event, it could be unanticipated rare event, but it could be very casual event in unexpected combinations of locations. That's what it is. There's another technique, which is mixing. I'm going to take scenarios that I thought of, and I'm going to mix them together into a single scenario. And the timing and the ordering of execution is going to be random. I didn't choose that. The technology chose that. And you're going to get multiple unexpected combination that will go beyond the thought out plan. I'm going to do that with the technology. Remember, this is still going to be high quality and legal scenario because all the rules are inside. So all these mixing are actually going to be legal, and I wouldn't have to spend a lot of time qualifying if this scenario makes sense or not. Let's look at an example here. This is a mix of cutting and oncoming. It's a scenario that we haven't seen. So I'm doing a mix here of oncoming and cutting and slow, and I put the constraint here that the color is blue, which is actually the color of my car. And here's how I'm saying, well, I want him to be in the same location because that's what I'm trying to do. I want to get the tension between these two scenarios. And now I can specify, this will ensure overlap between the scenario, but I can specify some synchronization rules about the overlap. I can say, well, I want the start of the oncoming to be at about the same time as the start of the change lane phase inside the cutting and slow, but it could be one, in the range of -1 second before or 1 second behind. But this is how I describe tight scenarios that will challenge my ego into some corner cases and scenarios I didn't think of. So mixes are very powerful. They're going to force the ego into some corner cases because there's going to be more traffic around the car. You cannot avoid getting out of risk so easily. And then I'm going to achieve this random timing and ordering for unanticipated legal scenarios. So this is about that. And let's move. I'm going to take you right now to a short demonstration. Now we don't have a lot of time, but we will give you a sample of each one of those phases that we just described. So I'm just calling fortify and activating the cutting and slow. Let's go and do it right here. So I'm selected some test and I set the seed. And this is the main GUI of Fortify. This is where you're going to see the source itself. This is the log terminal, and I can put commands in here, and these are the loaded files. And what you see is a test here. So it's just one line, and we're working here with Carla, so I can load my favorite or my chosen simulator configuration right here. And then I'm going to import what the developer created for me, the cut-in and slow that we've just seen. And then I can just extend top.main, set them up, it's one line, and I can, decide to change that line later on to do the same cut-in on a different map. And I'm just executing the cut-in and slow, and let's do it together. I'm just going to run that scenario. Notice that I run on seed number 1. I can select whatever seed I want, and every seed will give me totally random, maybe expected, maybe unexpected scenario. So our AV car is now in red, and here's the cutting from the right in this case, and you'll see that we're cutting in like that, and the cutting car is going to slow in a minute, and our ego is trying to avoid a collision like that. So this is just one scenario, and there's a lot of debug I can do in here. Just one second. I can basically look at the scenario at the timing that was randomized, debug, see how far I was, in case of a crash, etc. So this is just one scenario, but I can change the seed, like we said, and just get another scenario going. So with seed of 6, I'm gonna do exactly the same scenario. I didn't touch the test code or the scenario itself. And now the tool is going to randomize legal scenario, and you see that the location is different. This time we're doing the cutting from the left, and we're cutting in. Obviously, when I run this in a long regression, I know, million of scenarios, I will suppress the GUI, which is not that interesting. So these are the scenarios, and I can run all of these and have full regression of automated scenarios. So let's look at our dashboard. This is the tool that you will use if you adopt this approach. You'll use that more than any other tool. This tool will reflect how much verification were you able to achieve. You can see it's a hierarchical map of your verification plan. And you can see that the total score you got is 73%, but you can see each one of the subsections, how much it got. And you can see that we're playing here with colors. So it's very easy to see that this was never tried, and these are partially tried, and how much, what extent they were tried. So we can just, let's look at the cut-ins. For example, I can explore right now to see, here's the cut-in, there's subcategories in here, time for change. Let's look at that, time for a change. And you can see that we didn't try aggressive cut-ins, and there's some other cut-ins that we haven't tried. So I may want to create very easily to put another rule, hey, make more aggressive cut-ins, because that's what I want to get. And I can just look at the other scenario. Let's look at the curved lanes and see what's going on here. Again, I can fold and unfold, and let's look at the road curvature. And you can see that we tried straight roads, but not different kind of curvature. So probably, maybe I want to use different map. Maybe I just want to ask for different location to hit those scenarios and create quite a few of them. So here's where you get to see where you are, and basically ask the technology, please create more of these, and be brave. You can ask for a lot of these because it's automatically going to create some scenarios from you. Now, from the same very dashboard, I can look at failures, and here's some failures that you tried, and you can see the seed on which they appeared. And I can, if I want to debug one of these, I can just take the data with me, go here and just execute them. So the same test with the same seed will give me exactly the same response, assuming that it's the same software and same DOT taking the same reactions. So we're basically trying here another scenario. I may not even know what it does. This is a huge regression. Maybe I didn't create the original test. I'm just executing it, and I want to see what's wrong. Why did we fail? And here's a scenario that we have right now. In this case, it's a merge. It's a merge that we're seeing. So the AV right now is on green, driving here. You see the other car Larkin. Keep in mind, this is a random location, right? The tool chose the location itself. And this is an interesting one. It was merging through a gas station. And actually this one causes a collision. This is actually a scenario that we tried with real user and to expose the bag. So this randomness really doing the work for you. And this scale of tests that you can produce does do the work for you. So let me show maybe one more example. I want to show an example of mixes, but maybe some kind of a different flavor of mix that I didn't cover yet. I didn't cover yet in the slide, just to show you more of the capabilities here. So here's the mix that we have right now. It's still a mix of a cut-in and oncoming, you know, the same mix, and the color is blue and the path is the same. But notice what I'm specifying here about the overlap. So I want the oncoming scenario to start -1 or 1 second before the cut-in, and I want to specify the end that it will finish -3 to -1 second after the cut-in. So I can control the overlap and how exactly I want to get things done. And this is the place in which I use my gut feeling, right? Here's where I think the bug is going to be, and I'll control the ranges. I can put coverage on these ranges. Well, have I tried these kind of ranges or that kind of, you know, that range is important for me, or that specific value, maybe the min value or the max value, that's important. And I want to sample a few in the middle. So that is a habit that we do a lot. So if you have a huge range, well, get some of the edges and get some medium, small, and max, and have the technology try all of them. So this is what we're doing right here. And let's look at the example. And here is the cut-in. Our ego is in red. It's going to be the cut-in, and here's the oncoming at the same location. Look, this happens right in front of a bridge. Again, might be very interesting to try that, the visibility in this kind of scenario. So that is pretty much the end of this short demo, and I think we got you to demonstrate everything that you might want to do. So first of all, create scenario that's very easy, that's very short. Look at the coverage, look at what was achieved, what was actually achieved, steer the randomization, add mixing, have the technology surprise you with the kind of scenarios you didn't think of. And this is the end of this demo. And with that, I'm going to stop sharing, I guess, and let Yoav take over. It's all yours, Yoav.
Thanks. All right, so hi everybody. Thanks for joining. I'm going to go through recent language development and some stuff regarding the ASAM standardizations that Sharon has already mentioned. So Sharon has talked in general about the where the language is now. In other words, where the open language reference manual is now. And I'm going to talk about new stuff. Some of it is already in the FAQ that is on our web, but some of it is not yet. And hopefully it will get into the OpenLRM in the next few months. So first, let me talk about where those requirements are coming from. So many of them are coming from just Photonics customers, you know, from L2 to L4 and multiple market segments. I'll talk about market segments and their strange and different needs in a minute. Then there's this whole ASAM connection I'm going to talk about. There's an M-SDL partners program. Karen will show a link to how you can join that if you feel like it, and other influences. And I'm going to talk about a bunch of language developments. There's more than these, but I'm going to talk about how to create more flexible actor or scenario definitions. That will be the issue of conditional inheritance. I'll talk about checking and KPI definitions. And by the way, I've seen some questions on the QA box, so I'll try to answer them as I go. And I'll talk about user-defined topology. And then I'll also talk about some new capabilities that are enabled by the power of this language, like easier test writing. And the unifying theme here is language-enabled automation. So verification is hard intellectual job, however you look at it. And, you know, good people are expensive and hard to find, and computers are cheap, basically. So you really want the language to be aligned with your use case, not stop you, make the, you know, remove as much of the unneeded complexity as possible. All right, let me talk about this ASAM thing. Sharon has already mentioned it. So there's this OpenSCENARIO 2.0 concept project that was done already, and it's conceptually aligned with M-SDL. The concept document, which was published February, uses M-SDL for all examples, and it shares M-SDL's high-level goals of being powerful, readable, composable, declarative, portable, and open, the ones that Sharon talked about. And the standardization project itself has just begun, and I urge you guys to join if you feel like it. And they are targeting quarterly updates. Let me also say that I'm not talking for ASAM. Those are mainly my own views that you'll hear here. We are influenced by what we hear from ASAM, but I'm not, you know, a speaker for ASAM. So the concept project has already influenced. If you looked at the language about a year ago, the current language is different. So it has this Python-like syntax because we were asked to do that, or there was an intuition that we should do that. Some terms like actors and so on are now different, and so on. And the standardization project and the requirements coming from OpenSCENARIO 2.0 are influencing a whole bunch of new language developments. And those are mainly the ones I'll talk about now. So like multiple orthogonal ways to categorize vehicles. So for instance, there's a subgroup called the domain model group in this standardization project, in the concept project as well, that looks at how to define, what's the right way to define the library of objects. And they need a way, they were fairly clear about it, they need a way to say, oh, there's various kinds of vehicles like, you know, truck and car and bus. But at the same time, you also want to splice them another way and say there's emergency vehicles and non-emergency vehicles. And this is sort of orthogonal to the fact that they are a truck or a bus. So there's a need for such a thing, and I'll show how it's done. Then there's a need for user simulator vendors to extend everything and say, oh, my simulator supports only this, or that. I'm sorry, or does not support that. And there's a need to specify KPIs and checking and so on. There's some other influences on the language that I want to talk about. So there's all these market-specific scenarios, like customers are developing AVs for ports or mines or delivery bots or whatever, and they want to express themselves, they don't expect anybody else to do it, their own market-specific scenarios, like hook my trailer or whatever, and mix them with other scenarios like the cut-in that Sharon has shown you. And then ADAS developers want to test driver interaction scenarios, like what happens if the driver requests something or takes control or does not take control, and mix that with other scenarios. The other fairly big influence on the language is the need to refer to all of those ODDs, operational design domains. So customers need a precise way to define what an ODD is. Then they want to intersect that with a set of scenarios. In other words, to say, okay, of these 20 scenarios, I only want to run the chunk of them that is within the ODD. Or actually, very differently, they want to say, hey, I want an out of ODD scenario. What happens if suddenly I get into snow and that's outside my ODD, and how do I get to the minimal risk maneuver and so on? So there's a lot of testing space around that. And finally, there's a need for easier test writing. Many test writers are not programmers. That's a different skill set. And the language should allow you to move easily between levels of abstractions and should allow you to do fill requests very quickly. I'll show what that means in a little bit. All right, so let me go into that first topic, which is more flexible actor and scenario definition. So need number one is you want to randomize from a hierarchy of actors under constraints. Need number two is do multiple orthogonal actor dimensions like I was previously mentioning. And need three is do it all in a modular way. And the solution is something called conditional inheritance and something called extend. Let me go into that. So let's talk about randomly choosing from a hierarchy of objects. So let's assume we have a hierarchy like this, the one we see here on the right. So let's say we have something called traffic participant. That's the name that was at least temporarily chosen by the ASAM domain model group. And underneath it, there's like a vehicle and a person and an animal. Those are all traffic participants. And a vehicle can be a truck or a scooter, and a truck can be, I mean, you get the idea, right? And the point is, you may want to write a scenario like this one that says somebody crossing, where we have T of type traffic participant. And then we want to say, my ego is driving on this path, and this T, this traffic participant, is crossing it, as in this little picture here. And we want T by default to be randomized to be a trailer truck or a deer or a person or whatever. And then you may want to constrain it further. So later you may want to say, wait, I only want either a truck or an animal. So, you know, just these two branches of the tree. Or you may just want to say, hey, forget about traffic participants. I just want a truck. Okay, I want to do some truck related stuff. The second need is to talk about multiple orthogonal dimensions. So as I was previously mentioning, you know, vehicle, under vehicle, say, you want to say dimension one is truck and scooter and sedan, and under that there's simple truck and trailer truck and so on. But then there's this other dimension, like emergency vehicle or non-emergency vehicle, and another dimension, which is like electrical vehicle or internal combustion vehicle, and those are all orthogonal. So you may want to say, you know, I have a truck, but it's also maybe an emergency vehicle or not. Or if you say something is an emergency vehicle, it could be a truck or a scooter and so on. So, and again, you want to write, this is the old scenario I've shown you a few minutes ago. You may want to say, hey, this traffic participant can be a deer or can be a trailer truck, which is also an emergency vehicle or not. So by default, you know, all of these will happen. Or you may want to say, oh, today it's an emergency vehicle. And by the way, emergency vehicles may have their own behavior. So like if it is an emergency vehicle, then maybe it has a further attribute saying, oh, are the emergency lights flashing or not, right? And you do want all of these dimensions because they count, because those are variations that may get you some of your unknown scenarios that you didn't think about, right? So you just want to write a few lines and make all these variations happen. All right, so now let's go a little more technical. Hope you guys are all still awake about how you even write that. So most of you know what inheritance is, right? So you know, vehicle can inherit from traffic participant and truck can inherit from vehicle. It's a kind of vehicle, right? And what we're talking about here is similar. It's good old inheritance, but with a twist. So here's how you do it. So you define the traffic participant, the actor, which is traffic participant, and you define it a field, which I'll call the determinant field, okay, of type. It's an enumerated type, let's say it's a vehicle or person or an animal. Now, here's the important point. Then you define the actor vehicle as inheriting from traffic participant, but only if the kind field is vehicle. And similarly, I mean, if it's a person and so on, that's another type. So it's a type that depends on a value. And then a step down, you say, okay, a truck is a vehicle if the V kind field of that is a truck. And so on. I mean, you get the picture, right? So you just define determinant fields and you say, I inherit from it, but only if that value is so. And now you sort of get how this original scenario of mine would work, right? So you essentially, you know, all of these fields are randomized. Everything in a scenario, unless you say you give it a constraint, is randomized. And so the TP kind of that traffic participant will be randomized. If it happens to be a vehicle, then that's a vehicle. In which case, we'll randomize the V kind, and if it's a truck, then it's a truck, and so on. So that's the trick behind that. Now let me talk about how you add multiple dimensions. Okay, so I already have a vehicle. I add yet another field to it, which is emergency vehicle. It's a Boolean, so it could be true or false. And then I define an emergency vehicle as something that inherits from is emergency vehicle if this field is true. And again, you know, as you generate this scenario, this will become sometimes an emergency vehicle and so on. Finally, within this series about this conditional inheritance, let me talk about how to do it all in a modular way. And the example I'm going to use is encapsulating simulator-specific definitions in a separate file. So let's say we have all of the stuff we've written previously, but now you have a specific simulator that supports things that others don't, or doesn't support some things that others do. So here's how you go ahead and do that. Here's how you say, oh, my simulator supports also buses that you never talked about. You just extend that vehicle kind. You can extend both classes and enumerated type. And you say, oh, I add another enumerated type to it, another value, which is bus. And then you say, okay, I now define an actor bus, which is a vehicle when the kind is a bus. And from that, that's all you had to do, essentially, to make any scenario that has a vehicle in it to sometimes be a bus. Obviously, you have to then connect. This assumes that your simulator even knows about buses, and there's an interface to simulators. I'll talk about that later. Where you can, you know, connect that to actually have a bus appear in your simulator. But language-wise, that's all you have to do. Similarly, that's how you say, my simulator doesn't support scooters. So just adding that constraint will cause it such that anything that mentions a vehicle will never be a scooter. And if you specifically ask for scooter, you'll get a contradiction error because we can't do scooters on this simulator. Similarly, you can say via a constraint, you know, if it's an emergency vehicle, then it's not a truck because we don't support emergency trucks. Or you can say, you know, this particular simulator has another attribute that is not in the standard library, so to speak, which is, say, a wheelbase. So you just add that and you write in your simulator how you handle that. And suddenly all of your scenarios that talked about vehicle support that. Okay, so let me just summarize inheritance. So we've talked about conditional inheritance. It allows for very precise control via those determinant fields. It lets you specify which features are orthogonal to each other. Simply, they use different fields. And you can constrain, you know, what is it that you support by putting constraints on these fields. And there's also a way to do a conditional inheritance of scenarios, not just actors, but I won't talk about this because we don't have time. Extend is similar to inheritance, but it does not create a new type. Like we've seen on the previous slide, it just extends every instance of the original type like it was written in the original file. The reason you don't want to write it in the original file is because you want to do it in a modular way, right? You want to have a file called, you know, mysimulator.sdl that contains all the dependencies, all the stuff that is specific to your simulator, or that simulator, or one of the 5 simulators you're using. And then you just load it, and all your scenarios auto-adjust. And M-SDL also supports regular unconditional inheritance, but we won't talk about it now. All right. That was the first part. Now let me talk about flexible topology definition. So the current LRM already is fairly flexible with how you can define topology and roads and stuff and request what it is that you want to drive on, but it's not enough. So turns out users want to easily refer to absolutely any abstract map features and put constraints on them. So they want to say, hey, I want any 3-lane highway for this scenario or any T-junction. So in this new topology, that's how you say that. Or in this new syntax, that's how you say that. You define a field of HW of type highway and you put constraint on it. You say, hey, number of lanes is greater or equal 3. And then somewhere in the scenario, you say car 1 drive with the path being that object, which is a highway with greater or equal 3 lanes. All right, turns out users want to use their own abstract map features. This was actually perhaps surprising to us. There's all kinds of maps in this planet, and people want to say, hey, I have a forest map, or I have whatever, a lake map, and I want to say this scenario, use any road that runs along a tall forest. So they have like attributes to forest. Or use this specific kind of a tunnel. So this clearly calls for some user customization. And those features don't even appear just on OpenDrive maps. They can appear on anything at all. So, and you may need to collect them from multiple maps. So that's how you do it. You essentially define a new object, say a forest path, which inherits from road element, which is like the base of this. And in it, you can define any attributes like the height of the forest. And then you write procedural code in Python or C++ or whatever that extracts those from a map and associates them with the roads. And then, just like I've shown at the top, you just say, okay, I have F, which is a forest path with the height being tall or whatever, and then just drive along that. So that's how you can customize it to any kind of feature. And what I've seen, and I think that was one of the questions on the QA box, is how realistic are things? How can you customize it to whatever people want? So that's one way. If you're interested in forests or any kind of map feature that nobody else thought about, that's how you do it. All right. That's another topic that was asked on the QA box. How do you write rules? How do you check stuff? So let me talk about that. So users want actually two separate things. They want a way to record KPIs or key performance indicators for offline analysis. I'll show how you do that. And then they just need to do on-the-fly checking. So here's how you record KPIs. So you extend, say, our scenario, good old cut in and slow scenario, and you say, the time to, you define a field, time to collision at the end of change lane, that's just the name. And you say, this is, sample this particular expression. In this case, it's like the ego's time to collision to car 1 at a particular moment at this event, when like at the end of the change lane phase. And then you can say, record it with this text. And record means write it to disk for later analysis. So that's very similar to the cover statement that Sharon has already shown you, but with a slight distinction that cover says, use this parameter to see how well we have covered the scenario space, whereas record says, record this parameter to this so we can later analyze like what was the smallest or biggest within some set of runs. And the other thing you may want to do is just, if a KPI crosses some threshold, I just want to issue a device under test error immediately. That's how you do that. So you say, again, you extend cut in and slow, and we use the same time to collision field that we have sampled above. And you say, if that field is less than 0.7 second, then it's an error. That's an extremely, the most simple kind of a error message, and you can put it, or check, and you can put it in either in the scenario itself or in a generic place for all scenarios. And you can do much more sophisticated temporal checks, like during scenario X, if Y occurs, then Z should occur within 3 seconds. And there's some example of that in the FAQ on our website. We'll send a pointer to that with the presentation for everybody to see. Right, let me go to the last topic, which is more intuitive test writing. Sean has touched on that a little bit. Many developer groups have separate test writing teams. They often use a GUI-based editing tool. So if we look at this scenario where there's a cut-in combined with somebody coming from the side, there's actually fairly impressive tools where you draw that and set triggers and make it go, and it happens. And you can, we have some experience. Usually you can take those scenarios and auto-convert them into M-SDL. They're stored as XML or whatever they're stored in. But what happens is those scenarios are extremely directed. So this is just an example here. It says, you know, there's a truck 1, which is blue, and a car 2, which is green, and then use this specific map. And here's the explicit path. There is a way to say that in M-SDL, you know, go through exactly these points on that particular map, and then everything is very specific. Sometimes ranges are allowed, but without constraints. It's usually best not to, so it's very useful, but it's usually best not to start that way. In other words, it's a lot better if you write very generic scenarios like the one here, which is similar to what Sharon has shown you, and run it many times or constrain it to be more specific. And the language, of course, supports multiple levels of abstraction, so you can do whatever you want, essentially. My next point is about more intuitive and powerful test writing. So you want to take, again, the scenario of somebody cutting in while somebody is coming from the side, and you want to fill very quickly this huge coverage space of all the various dimensions. But the issue is that a lot of the pieces there are indeed illegal or not interesting, and people spend an awful lot of time removing those. And it's very important that you'll be able to automatically remove them. And a powerful language enables simple tools. You want coverage definitions to allow the automatic filling, and I'll show that in a minute. You want constraints to do easy filtering, and declarative language to allow visualization. So let me talk about a tool that we've created here in Fortelix. So that's not a language feature, that's a tool, but I'm using it just to demonstrate how relatively easy it is to create such things if the language is the right one. So it's a spreadsheet kind of a tool. You essentially fill a spreadsheet. And then, like, if you look at the table above, each line represents many combinations of this scenario on the lower right. Like this particular line says, you know, run 5 times starting at seed 3 using simulator sumo and using map 1, and you know the cut-in is from the left as we see in the picture here, and the ego direction is straight, and so on. And if you say fill, that means you know, fill all the possible combinations that are defined in coverage for that. And if you do multiple fields, that means all of them. And turns out people are already comfortable with spreadsheets. You can copy and create these very quickly. And you can say, okay, send all of these many, many runs for batch execution, or you can say, you know, just run interactively this particular line. And if you look at this line that says fill, 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 there's really like 120 tests here. You know, like there's 10 maps, and you can go left or right, and you know, the car could go straight or left or right at the junction, and so on. And it also says run each of these 100 times. But how do you do the removal? Let me just walk very quickly through that because we're out of time. So again, looking at that line, there's about more than half of these combinations are things you'd like to remove. Like, let me walk through them. This one, you know, if the cut inside is right and the ego direction is right, is physically impossible. Because if the AV is turning right, then, you know, the cut-in car has nowhere to be to the right. And that will automatically be removed because just physical constraints will remove it for you. You don't have to say anything. This is not interesting because this guy is going left and this guy is going right. So they're not even coming close. You'd have to write a constraint saying, remove that because it's not interesting. And here, you know, these combinations are not interesting because, are impossible because there's just no such junction on the map. So anyway, let me go to my summary real quick. We try to show you that the language is powerful, readable, composable, and so on. The language is still evolving. We think it's in reasonably good shape, but it's still moving. I've shown some recent developments and where they come from. I expect the ASAM interaction to continue influencing the language and customer interactions as well. Thanks for everybody who contributed, and we need more feedback, absolutely. And like I said, we're working on a new version of the LRM. And with that, I'll give control back to Karen for the Q&A session. Karen, go ahead.
Thank you, Yoav. Before we get started with our Q&A, I would like to briefly introduce our company. Fortelix enables measurable safety of ADAS and autonomous vehicles. We develop a platform called Fortify for intelligent verification, automation, and analytics needed for moving from ADAS to ADAS Plus to autonomous vehicles. Fortelix's solutions range from a cloud-based scenario deployment solution, highway simulation-based verification and validation, to tailored verification and validation solutions for urban, confined areas, and more. Fortelix's solutions come with the proven, measurable, coverage-driven verification methodology. They provide tools for exposing bugs, unknowns, and edge cases, and make the verification and validation process much more productive, significantly reducing the risk of failure. And now, I would like to introduce the ways to keep in touch with us. So, on the left side, you will find various options to be involved and influence the development of M-SDL. First of all, if you haven't done so already, you can find the language specification and other materials on our website. We then welcome your comments and questions about the language to msdl@fortelix.com. And we also have a partner program for M-SDL that allows companies to get earlier releases of future versions of the language, as well as closer cooperation. On the right side, you will find all the ways to stay in touch with our news and updates, including Yoav's blog, our active LinkedIn page, and newsletter. And last, today you have seen the M-SDL language running on Fortelix's Fortify solution. If you want to explore M-SDL, the Fortify technology, for your specific challenges and needs, please contact us at info@fortelix.com. And now, for our Q&A. Sharon, do you want to take this first question?
Yeah, and let's do it like that. I'm gonna pick up the hard questions to answer. So there's many, and leave Yoav the easy one. So, for example, there is a question: can we get the slides? And the answer is yes. You're able to get the slides, and Karen will share it with all of you. Yoav, should I continue, or you go ahead and take the next slide?
Let me do some. So, you know, a bunch of questions about simulators and how do I use my own simulator versus. So let me just make that clear. Maybe we didn't clarify at the very beginning. So we talked about the M-SDL, the language. Then there's and the language is supposed to be simulator independent. We specifically at Fortelix, the company, we don't do any simulators. So we connect to other people's simulators. And one of the questions, if we are using an in-house simulator, how will this work? So very specifically, there's an interface document that says, how do you connect to any simulator? And essentially, and it's fairly easy, but I mean, that still work, and you can connect, and we have a whole bunch of people who connected this to their in-house simulators. That ties to another question about the realism of the simulation, and that was mentioned actually, I think, by several questions. How realistic is the simulation? How do I use my own behavioral models or driver models? Those are somewhat related because we can create those scenarios, but essentially we act as the puppeteer, so to speak, talking to the simulator, and the realism depends on the simulator. So as far as the scenery is concerned, or how good is the sensor simulation, that obviously depends on the simulator. And part of it depends on driver models or external driver models. So people have either their own, machine learned driver models or whatever, or they buy them from elsewhere. And those are fairly realistic. And the question is, how do we connect to them? And I'll just answer that very briefly. And if anybody wants more answers, just send an email to info@fortelix.com, and I'll be happy to answer it. But essentially, you've already seen conditional inheritance. You know about it. So what you can do is you can create yet another orthogonal dimension, which says which model it is. Okay, this is my machine learned model, or this is my C++ model, and so on. And then when we send the request to that car, you can customize that model to send a request to that model, assuming it supports those requests like change speed and so on. And there's a way to also specify I do not support that kind of a request. I've shown a little bit of that. So somewhat shorter answer is there's a way to connect to arbitrary behavior models, and then the fidelity of the result and how good it is depends on that model, essentially. I've talked a little bit about checking. There's a bunch of questions about how hard it is to check and how do you check rules. And I've shown a few examples, but I've also mentioned that there's a way to check more complex temporal things, and I'll be happy to get more information, tell you more information about that. And I also just want to mention that in general, as a methodology, you would like to put as many of those checks in a global place such that they are scenario independent, but sometimes you cannot. In other words, sometimes you must have those connected to a specific scenario because you want to connect them to the behavior of that scenario, and you can do either. Sharon, do you want to take it from here a bit?
Yeah, there is a question, and you may touch that, Yoav, how do you define the criteria to market scenario as passed or failed? And there's two ways to interpret the question, and you kind of answered the first one. So the language allows you to check that, and you can take into consideration, well, if the distance was like that and relative was like that, then this is an error. Otherwise, it's not an error, that is okay. So you can tailor your checks to see if the ego was properly reacting. But there is another meaning of pass and fail. So sometimes you want to get a scenario, and we will plan the scenario and we will adjust. Remember those runtime adjustment? We're going to adjust the speed of the other surrounding cars to try to nail and create what you wanted. But the ego can do very extreme things, and maybe it will stop or take a U-turn. And then the scenario never succeeded. We never nailed the intent, the high-level intent that you were shooting for. So this is a different kind of failure. We're just telling you, we're not able to accomplish what you wanted. And you may want to try to run it with a different variation, and we may be able to do better on that variation. So these are two kind of failures. One is the ego didn't properly react, and the other one, given all the runtime adjustment, we were not able to reach it. Here's what you got, and try again. So that is the answer to that one. Yoav, want to pick?
All right.
Pick one?
So there's a bunch of questions about maps. So let me just read out one. So you use Scala as a simulator. Do you have a generator which also generates an appropriate XODR file for the scenario you describe in M-SDL? So let me just clarify. The language itself does not specify, I mean, when you describe that, hey, I want this to be in a junction, or I want this to be on a 3-lane highway, there's really two ways to achieve that. One is automatically create a map that has a 3-lane highway, and the other one is search on a bunch of maps that are given by the user for a random place which has a 3-lane highway. The language, as it is defined, supports both users. We've only done the second. It turns out that most people, that's what they want. They just want to give a map corresponding to their ODD and say, okay, find randomly all the places, each time instantiated on that place in the map. So the language allows, automatically creating a map from description, but we never did it. Let me very quickly find another one here. There's a question about, in general, how do you, so let me just read it. A scenario written in M-SDL implicitly, explicitly determines an environment feature space to explore. As you randomly create a variety of scenarios belonging to this space, you have a notion of coverage on this space. So to a large extent, the way to cover it is using those cover statements that Sharon talked about. In other words, you usually within a scenario, you say, okay, here's the dimensions of that scenario as like this cut-in and slow, has the side, has whatever parameters. And essentially, what you do is you define a coverage space via cover statements for that scenario. And that coverage space could have, would have whatever, 5 to 20 bucket items in it, and each has a bunch of buckets. So you're ending with a coverage space which is whatever, from 100 buckets to 100,000 buckets. That's a fairly large range, and it determines what this scenario, what's the space of this scenario, and to some extent the decision of what to define, to use, and what to cross with what has to do with your intuition, with what you are afraid of, and so on. And then if you have a bunch of scenarios, each would have a coverage space like that. So that's how you would go about defining that and then tracking it using this analysis tool that Sharon has shown. Sharon, do you want to take one?
Yeah, there's a question about the example of a rule. Maybe that was asked before I covered that, and maybe I just did a lousy job in describing it. So let me give an example. For example, you have a cut-in scenario, and you would like that within one of the phases, the speed will be within certain amount of kilometers per hour. That is what we call a rule. That is a constraint, and you can express that with a keep constraint or another modifier like we did with the speed modifier. This implies constraint. I would like the speed to be between these boundaries. Now the tool will check that request that you did for a rule and will tell you, well, can I do it or not? Sometimes you're asking for something that cannot be done because within that phase, the speed should be, I don't know, between 20 and 30, and you ask it to be 80. So that's inconsistent with the definition of the scenario or the nature of the car or whatever it is. So the tool is first going to validate that constraint, what you're asking for. And if there is a solution, it will give you an answer. Here is a full concrete scenario solving all the dependencies, the ones that you just asked and the existing ones, into a coherent, consistent scenario. And you can make, you can ask for a specific one, a random one, or exhaustively cover all the possible scenarios, taking into consideration that there could be multiple ones. So you can, with a field request, you can ask, well, give me all of them or all the combinations, etc. So this is what we call a rule, and it could be done with a constraint or a modifier. Do you have time for more?
Yeah, I think we have for one or two more. Do you want to do them, or do I do it?
No, whatever you want.
Let me just go through this one that I have right here that may be interesting. It looks like there's a way to specify constraints on longitudinal acceleration of a non-ego vehicle. Can I similarly constrain the lateral acceleration? And there's a related question, is the set of parameters, speed, change speed, color, and so on, fixed, or is it defined by the simulator? So that goes to sort of an important trade-off that I sort of mentioned before. So yes, there's also a lateral acceleration modifier because people wanted that. But in a sense, there's a way, and I haven't talked much about that, there's a way to add whatever it is that you want. So not only do you want to add, you know, attributes and restrictions for simulators, simulators have a way to say, you know, I want the rate of whatever, or I want to control the yaw, I want to do whatever. And there's a way in the language to extend the set of modifiers and set of constraints and add a new one, as long as, you know, your simulator knows how to handle it. Now that I've answered something positively, let me answer something negatively. It says, is it possible to integrate sensor front-end models like LiDAR into M-SDL? If yes, could you please explain the interface integration process? So the short answer is, we don't do it. It's something that the simulator does. We have, or I should say, M-SDL has a way to influence that. Like if you want to insert errors into that, then you can create a white box hook into M-SDL, which says, you know, change that or whatever, but the heavy lifting there is on the shoulders of the simulator. I think we're running out of time.
Karen, do we have time for one more, or should we conclude this part?
I think one more is okay.
Okay, so let me pick that up. There's a question, wouldn't it be more natural to describe cutting scenario in all serial manner? Why combine serial and parallel? So you can define it the way you want. So, but for sure we want the ego to be driving and the cutting car to do things, the other car to do things around it. So there's parallelism involved, and we did it like, oh, for each phase do parallel, the ego is driving and the other car is doing something else. But you can create your own scenario topology. We could have done, oh, parallel, get the ego car to drive, and then serially the other car will do phase one, get ahead, and then slow, do the cutting and slow. So you can define it, and the tool will be able to accomplish what you're asking for. If it's more natural to you, the answer is yes, you can do that. There's one more. How does the new conditional inheritance compare with standard C++ or Java inheritance? There's multiple differences. I guess the biggest one is that if you're describing things in C++ and you're going to allocate or randomize a class, the parent class, like a vehicle, you're going to get a vehicle. You're not going to get one of the derivatives. And this is what we want to get. We want you to have a reference to a vehicle, and randomization will take you to one of the subtypes, one of the children classes. So this is what we want to, and that's going to be randomly selected. And like you have said, you have the determinant field to say what do you want, from which ranges do you want to get it, etc. So that is about that, and I think we're done. Karen?
Okay, and with that, we're at the end of our webinar. I would like to thank our speakers and also want to thank our audience for joining us. We will send a follow-up email with the presentation and video from our session next week. We encourage you to contact us through the different channels for staying in touch. Thank you and goodbye.
Thank you. Bye, everybody.
Thanks.